Hello viewers. Welcome to the YouTube channel. In this video we will study lecture 4 of class 12 chapter, Current Electricity for board, NEET, CET and JEE. If you have any doubts please comment or join the Telegram channel. Lecture 1, 2 and 3 video link is given in description. And don't forget to subscribe the channel. Let's start. In metals, number of free electrons per unit volume does not depend on temperature, but in semiconductor and insulator, number of free electrons per unit volume depend on temperature. Temperature dependence of metals. Resistivity of metals is directly proportional to absolute temperature. That is, as temperature increases, then resistivity also increases, as shown in figure. The variation of ρ with T is as shown. Resistivity of a conductors increases with increase in temperature. ρT is equal to ρ naught into bracket 1 plus alpha into T minus T naught, where ρT is resistance of conductor at temperature T. ρ naught is resistance of conductor at temperature T naught. Alpha is temperature coefficient. Next, temperature coefficient of resistivity of conductor. It is defined as the fractional increase in resistivity per unit increase in temperature. Alpha is equal to delta ρ by ρ naught by delta T. Therefore, alpha is equal to delta ρ by ρ naught into delta T. SI unit of alpha is per Kelvin. Practical unit of alpha is per degree Celsius. And alpha is positive for metals. Note 1. We have RT is equal to R naught into bracket 1 plus alpha into T minus T naught, where RT is resistance of conductor at temperature T. R naught is resistance of conductor at temperature T naught. Alpha is temperature coefficient. 2. For some alloy like nichrome, alloy of nickel, chromium and iron, manganese and constantan exhibit a weak dependence of resistivity with temperature. That is, resistance and resistivity would change very little with temperature. And temperature coefficient value is very small. Thus, these materials are widely used in wire-bound resistors. Since their resistance values would change very little with temperature. The variation of resistivity of alloy with temperature is as shown. 3. In insulators, ρ decreases with temperature T increases. Next, temperature dependence of resistivity of semiconductors. For semiconductors, resistivity decreases with increase in temperature as shown. That is, alpha is negative for semiconductors. In semiconductor, as temperature increases, the number of free electrons and holes per unit volume, N, increases. Therefore ρ decreases. That is, ρ inversely proportional to N. Next, we study about series and parallel combination of resistors. 1. Series combination of resistors. The two or more resistors are said to be in series if only one of their endpoints is joined such that current through each resistor remains same. 2. Parallel combination of resistors. The two or more resistors are said to be in parallel if one end of all the resistors is joined together, and similarly the other ends joined together such that potential difference across each resistor is same. 3. Equivalent resistance. A single resistor which produces same effect as that of set of resistors is called equivalent resistor and its resistance is called equivalent resistance. Next, derive an expression for equivalent or effective resistance of two resistors connected in series. From the figure, A and B are two resistors connected in series. R1 and R2 are resistances of A and B respectively. V1 and V2 are potential differences across A and B respectively. V is potential difference applied across the combination. I is current in the circuit. In series combination, current remains same. Rs is effective resistor of resistance in series. In series combination, potential difference applied across the combination is V is equal to V1 plus V2. Mark as equation 1. According to Ohm's law, V is equal to IR. So we have V1 is equal to IR1 and V2 is equal to IR2, where I remains constant in series combination. Substitute V1 and V2 values in equation 1, we get V is equal to IR1 plus IR2. Take I common, we get V is equal to I into bracket R1 plus R2. Mark as equation 2. If the combination is replaced by effective resistor of resistance, Rs, we get V is equal to I, Rs. Mark as equation 3. Now, substitute equation 3 in equation 2. We get IRS is equal to I into bracket R1 plus R2. Here, I will get cancelled from both sides. So finally we get Rs is equal to R1 plus R2. This expression for equivalent or effective resistance of two resistors connected in series. For effective resistance of three resistors connected in series, Rs is equal to R1 plus R2 plus R3. For n resistors in series combination is given by Rs is equal to R1 plus R2 plus R3 plus R4 plus, so on, up to Rn. Next, derive an expression for equivalent or effective resistance of two resistors connected in parallel. From the figure, A and B are two resistors connected in parallel. R1 and R2 are resistances of A and B respectively. I1 and I2 are current through A and B respectively. V is potential difference applied across the combination. I is main current in the circuit. In parallel, potential difference across each resistor is same. In parallel combination, I is equal to I1 plus I2. Mark as equation 1. According to Ohm's law, V is equal to IR. On equating, I is equal to V by R. So we have I1 is equal to V by R1 and I2 is equal to V by R2. Substitute I1 and I2 values in equation 1. That is, I is equal to V by R1 plus V by R2. On taking V common, we get I is equal to V into bracket 1 by R1 is equal to 1 by R2. Mark as equation 2. If the combination is replaced by effective resistor of resistance, Rp, I is equal to V by Rp. Mark as equation 3. From 2 and 3 we get V by Rp is equal to V into bracket 1 by R1 plus 1 by R2. Cancel V on both sides. We get 1 by Rp is equal to 1 by R1 plus 1 by R2. This is expression for equivalent or effective resistance of two resistors connected in parallel. For effective resistance of three resistors connected in parallel is 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. For n resistors, 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 plus so on up to plus 1 by Rn. Next, electric cell. The device used to maintain a steady current in the circuit is called electric cell. Example: electrolytic cell, Daniell cell, Lackland cell, dry cell. This symbol represents electrical cell. Next, electromotive force of a cell or EMF of a cell. It is the work done by a cell to drive a unit positive charge completely around the circuit. Therefore, EMF is equal to work done by charge. That is, EMF is equal to W by Q. SI unit is volt. Define the SI unit of EMF. The EMF of a cell is said to be 1 volt, when 1 joule of work is done by the cell to drive 1 coulomb of charge completely round the circuit. Therefore, EMF is equal to W by Q. Consider: if W is equal to 1 joule and Q naught is equal to 1 coulomb, so EMF is equal to 1 by 1, that is, EMF is equal to 1 volt. Next, look into electrolytic cell. Consider an electrolytic cell. It has two electrodes called positive, P, and negative, N, electrodes as shown. Here, V plus is potential difference between P and electrolyte, and minus V minus is potential difference between N and electrolyte. Therefore, potential difference between P and N is called EMF. EMF is equal to V plus minus of minus V minus. We get E is equal to V plus plus V minus. This is for open circuit. Let R is external resistance in the circuit. I is current flows through the circuit. V is potential difference across R. But I is equal to V by R. If R is equal to infinity, then I is equal to V by infinity is equal to 0. Therefore, circuit is said to be open circuit if no current flows through the cell. Next, internal resistance of a cell, denoted by small r. Definition: the resistance of the cell which opposes the flow of current through it is called internal resistance of a cell. For an ideal, R is 0. Next, terminal potential difference, TPD. TPD is the potential difference between the positive and negative electrodes of a cell in a closed circuit. In general, TPD is the potential difference across external resistance. SI unit is volt. TPD is measured during closed circuit. That is, when current flows through for closed circuit. R is not equal to infinity. Therefore, I is not equal to 0. The relation between EMF and TPD is E is equal to V plus IR. Next, derive an expression for current through simple circuit. Or derive an expression for current drawn by an external resistor and terminal potential difference. Proof: Consider a simple circuit. E is EMF of a cell. I is current flows through R. R is external resistance. V is potential difference across R. R is internal resistance of a cell. V dash is potential difference across small r. Therefore, potential difference across R is V is equal to IR. Potential difference across small r is V dash is equal to I into small r. EMF of cell E is equal to V plus V dash. Therefore, E is equal to V plus V dash. Substitute values, we get E is equal to IR plus I into small r. Take I common. That is, E is equal to I into bracket R plus small r. On equating to I is equal to E by R plus small r. This is expression for current through simple circuit. For terminal potential difference, V is equal to IR. Substitute I value, we get V is equal to ER by R plus small r. Note 1. If R is equal to 0, then cell draws maximum current. That is, Imax is equal to E by R. 2. For closed circuit, V is equal to E minus IR. Now, V is called terminal potential difference, TDP. Terminal potential difference is equal to potential difference across R, where R is equal to external resistance. In the next lecture, we see two more derivation on EMF and internal resistance. So don't forget to subscribe the channel for more.